Okay, I'm Young Kim. Thank you for giving an opportunity to talk about the laminar groups. The title is Groups Acting on the Circle with Invariant Laminations. This talk is related about the circle action. This work is joint work with Hyung Baek. First, let's begin with the definition of geodesic lamination. Let S be a hyperbolic surface. For example, genus 2 surface or hyperbolic surface itself. And a geodesic lamination on the surface is a closed subset with a disjoint union of simple closed geodesics. Not simple closed, simple geodesics. So for example, on the genus 2 surface case, a disjoint union of simple closed geodesics is going to be a geodesic lamination. And the Fourier diagram on the hyperbolic plane, which is drawn like this, which is consist of the infinity many ideal triangles. So these are the example of geodesic laminations. So each geodesic is called a leaf, and each connected component of the complementary region is called a gap. So here, the gap is homeomorphic to one pair of pants, and here a gap is an ideal triangle. So now I want to introduce some terminologies about geodesic laminations. First, let's lambda be a geodesic lamination on the hyperbolic surface. And first, if every wave is dense in the lamination, then it is said to be minimal. The minimality means that there is no sub-geodesic laminations. And second, if every gap is an ideal polygon, then it is said to be very full. So here ideal polygon means the finite-sided ideal polygon on the hyperbolic plane, which looks like this. So the first case is not very full. The second example is very full. And third, if there is no foliated disk on S, it is said to be totally disconnected. So our previous two examples are totally disconnected, obviously. But for example, let me show a known example. This is known example. Okay, here's our hyperbolic plane, and we fill the plane by geodesics, which are sharing a point on the boundary. And this set of geodesics gives a geodesic lamination on hyperbolic plane. And in this case, any open disk on the hyperbolic plane is foliated by the ellipse. So this is not totally disconnected. Now, I want to talk about the circle homeomorphisms. Our circle comes from the boundary of the hyperbolic plane. Now S is the Poincare disk. Here's our hyperbolic plane. So the boundary of the hyperbolic plane is homeomorphic to the circle. So any conformal map and quasi-conformal map defined on the on the Poincare disk can be extended on the extended continuously on the boundary circle, and by restricting them on to the boundary circle, they gives orientation preserving circle homeomorphism. So here homeo plus S1 denotes the set of orientation preserving circle homeomorphisms. So in this sense, PSR to R, which is the isometry group of the Poincare disk, so this group can be considered a subgroup homeo plus S1. And also, on the compact surface, and when we have some mapping class, then we can think about the universal cover of this surface. This is the universal cover is H2, and then we can think about the rifting of the mapping class element. Then this mapping class element gives a quasi-conformal map on the hyperbolic plane. So the rifting, so it gives also orientation preserving circle homeomorphism. So we can think this is also an element. We can think of this is also an element of homeo plus S1. So now I'd like to introduce the circle lamination. First of all, before defining the circle laminations, we need to translate the geodesic as a boundary object, boundary circle object. So when we have a geodesic, then it gives two boundary points, which is the endpoint of the geodesics. And conversely, any given two boundary points, for any given two boundary points, we can draw a unique geodesic joining them. So we can think, so now we define the set P2, which is, let's P2 the set of unordered pairs of distinct points in S1. This P2 has a natural topology, which is induced from the Hausdorff distance. And then now for defining geodesic lamination, we need to kind of disjointness condition of these 2 point sets. So for two elements A, B, C, D in P2, then we say they are unlinked if, okay, let's look at this picture. We have a geodesic, which is corresponding to AB, and also another geodesic, which is corresponding to CD. So these two, the corresponding geodesic are disjoint and linked. We say they are linked if they are if linked otherwise. Now we are ready to define the geodesic lamination. So a circle. Now we need to. Now we define a circle lamination. A circle lamination is a closed subset of P2 whose elements are pairwise disjoint, pairwise unlinked. So from the definition of circle lamination, it they circle lamination gives a geodesic lamination in previous sense, and also and vice versa. So if there is no confusion, we abuse these two terminology, geodesic lamination and circle lamination. But the reason why we use circle lamination, the notion of circle lamination, is we need to talk about the circle actions. And then now we define lamination groups. A lamination group is laminar groups. A laminar group is a subgroup of Homeo plus S1 preserving circle lamination. So the study of lamination groups is motivated by the work of Thurston. So Thurston shows the following theorem. The theorem says if M is a Tourette string manifold admitting a co-orientable tau foliation, then there exists a circle action of the fundamental group. So pi1 M acts on S1 act on the circle by homeomorphism faithfully. And moreover, in the proof of this theorem, we may observe the following things. This action also preserving a pair of circle laminations. So this is kind of so this gives a geolaminar group. So by definition, so first of all, I'd like to explain more concrete example of a Tourette string manifold admitting co-orientable tau foliation. So the most typical example is hyperbolic mapping torus. Let S be a closed hyperbolic surface and phi be a pseudo-anosable element in mapping class group of S. So the mapping tori is going to be a hyperbolic string manifold. And obviously, this mapping tori are foliated by their fiber. So that foliation is obviously tau foliation. So by the Thurston theorem, pi1 and phi act on circle, and moreover preserving a pair of circle laminations. So I'd like to explain what they are precisely. So here is our surface S. And then there is a homeomorphism, pseudo-anosable map phi. And then let's think about the universal cover H2. So the deck transformation acts on H2, and the rifting of any rifting of the phi tilde acts on H2, and these two things generate pi1 generate a subgroup which is homeomorphic to pi1, the mapping torus group. And this mapping torus group, as discussed before, we may think of this mapping torus group, mapping torus group as a subgroup of homeo plus S1. And also, the pseudo-anasub element, by the definition of pseudo-anasub, there is a geodesic laminations, invariant geodesic lamination on the surface. And the pre-image, let me write the covering map by by P. Let me write P for covering map, and the pre-image of these two geodesic lamination. Let me write P inverse or pre-image of lambda plus is lambda tilde plus, and the pre-image of lambda minus is lambda tilde minus. And these two pre-image are gonna be geodesic laminations on H2, and also by the definition, by the construction, these two lamination preserved by pi1 mapping torus group, and also this is the action which comes from the Thurston theorem. And here is the list of the properties which are satisfied by this action. So lambda tilde plus minus are very full, totally disconnected, and there's no isolated leaf, and pi1 s act minimally on the leaf space. And on each lambda tilde plus minus, gaps fall into finitely many OB classes. So this is the example. So this is the motivational example of the laminar group. So now we want to study it about the more abstract sense. In more abstract sense, the laminar groups. So now I'd like to define the type pairs. This is the just abstractization of the previous example. So because let's G be a laminar group and L be a lamination preserved by G, we call the group G the pair, type pair, if it satisfies the following. These 5 conditions are already we concerned with them. Okay, these 5 conditions, exactly those 5 conditions. So, but in type pair case, it is the group. We don't know the group is whether a manifold group or not. So we want to kind of we want to consider kind of inverse problem of the Thurston theorem when we have some kind of group circle action, and can we recover some kind of information of manifold groups or not? So as a evidence theorem, which is indeed the concept of type pairs was suggested by Danny Caligari, and in his unpublished manuscript. So in that manuscript, He showed the following theorem. Let M be a closed irreducible string manifold, and suppose that there is a good circular lamination which makes pi 1m, comma L be a type pair. If there are two gaps sharing a vertex, then M is Haken. So this show pi, uh, this from this theorem, we may guess that type pair is good at detecting a surface subgroup. So it looks like a type pair is kind of a geometric object. So so recently, Beck and I focused on the more basic property of the laminar groups. So recently, we could show every type pair is not virtually abelian. According to the teacher alternative in linear group case, if some group is not virtually abelian, and then it contains a non-commutative free subgroup. So we may expect some kind of analogical theorem. Fortunately, Margulis proved the following things. When G is a subgroup of homeoplus S1, then either there is a G invariant probability measure on S1 or G contains a non-abelian free group. So by using this theorem, we may show using this theorem, we may show we could show every type pair which satisfying some special condition has a non-abelian free group. So first, we showed if there is a G invariant probability measure, then the support must be 1-point set. So from this theorem, we can get the following corollary immediately. The corollary set type pair has at most one global fixed point. So usually the so if every if some type if a type pair uh, does not admit a global fixed point, then the type pair contains a non-abelian free group. This is a corollary from the previous corollary and the theorem of Margulis. So this, as a result, we could show kind of teacher alternative for type pair. So this is what I prepared. So thank you for listening.